Hi, and welcome to part 3 of the tutorial where we're going to model the Berlin Holocaust Memorial Museum. In this third part of the series, what I'm going to do is I'm going to follow the same logic that I followed in the past two tutorials where we modeled the whole monument with simple, regular, vanilla grasshopper logic. But what I'm going to do is I'm going to follow all that logic and I'm going to translate it to code that is written in C# using the Rhino common library. And then what we're going to do is we're going to create one large C# component that incorporates all the logics and all the parameters of the model. And then inside of this component, we're going to write the same grasshopper logic that we did before, but with plain, simple C# code. This has a lot of advantages. It's usually better in terms of performance, and depending on who you talk to, it gives you some more flexibility for certain operations. But it's definitely a good learning exercise if you're into computational geometry and you want to improve your skills when it comes to generating computational geometry again. So stay tuned and let's take a look at how we can do that, how we can recreate this monument with a C# scripting component. Good. So let's get started. As if you remember from the previous video, we implemented the full monument using regular grasshopper components. What we're going to do this time is we're going to implement the exact same logic, but we're going to write it in a purely C# using Rhino common and using a grasshopper script. So in order to do that, I'm going to keep this here so that we can go back and forth and see how things in C# look as opposed to in grasshopper. But I'm going to start my own parallel development thread, if you will, here on the lower bottom. So what I'm going to do is I'm going to bring copies of the three components that contain the geometry. So I'm going to bring those here. Those will be the top surface, the bottom surface, and the top surface, the bottom surface, and the curve. And I'm going to also copy paste like a bunch of these components, a bunch of these sliders for the size of the elements of the monument. Now I'm going to start here, and I'm going to drop a C# script component in which I'm going to add a bunch of the parameters that I think I will be using throughout this definition, and those will probably only be like a few, and then as I keep going I will add more inputs. So the first thing I'm going to do is I'm going to right click here and I'm going to add 5 inputs. The first one is going to be the boundary curve. The second one is going to be the top surface. The third one is going to be the bottom surface, bottomo, the bottom surface. Then, so I need to add more than 5. I need to add 6. Then I need to add gap in x direction. Or distance in the x direction. I would like to add distance in the y direction. I would like to add block width and block depth. So the 2 dimensions of each one of the blocks. Okay. I like being sort of descriptive about my variables. If you use BC, TS, BS, DX, DY, it gets a little confusing when you're writing inside, so I recommend, it's a good practice, the inputs of the components to give them like a nice descriptive name that is easier to recognize when you're writing your own code. This is going to be the boundary curve. This is going to be the top surface, the bottom surface, distance x, distance y, the width of the block, and the depth of the block. Okay? And something that you have to do always as well is whenever you write your inputs, you need to right click and make sure that the input access, so whether if we want just an element, whether if we want a list, or whether if we want a tree of elements, is correctly placed. Here we're going to be only working with item access, so by default everything is going to be good. But we also need to keep in mind that we need to specify what type of data are we plugging into that input? So for this one, here is going to be a curve. For the surface, I'm not going to use a surface, I'm going to use a vrep. And I will explain why I did that later in this video. So bear with me on this one. I'm going to use here a vrep. And then for distance x and distance y, I'm going to use doubles because I do want decimal precision. But then for the, wait, this is not block width, this is block count. Yes, sorry. So this is the count, how many elements there are in each count y, and then I'm going to add here another couple of elements, and this is going to be block width, and this is going to be block depth. All right, that looks much better. Okay, and then so as I was saying, for x, for how many elements I want in the x direction, that should be an integer because I don't want decimal part there. And for block width, I'm going to use doubles, and for block depth, I'm also going to use double. So with this, I think we're already, I just need to do this, guys. I'm sorry, I need a little bit of order. And I think with this, we're in a pretty good point to start going into the component and punching in some code, okay? Let's start. So I'm going to go into my C# script component. I'm going to double click here, and then I'm going to open the C# editor. Before I do that, I'm going to do something that I like a lot. I'm going to put a panel here on the output because the output is a really good place to look at where you have your errors and where something is not making sense for the C# compiler, and that's going to happen a lot through the course of this development. So I want to have a good grasp of like the console window that's going to tell me everything that I'm doing wrong, basically. I also want to use this to give myself some information here and then. So for example, something that I can do very easily to see if the component is working is that I can open the component and I can just type print, and then for example, hello Berlin, and that's it. And then I can run this component and I can see that the component is outputting this string that I just created. So everything is working well. So I think we are good to start. Now, what is the first thing that we can do? I think I'm going to follow a similar structure on the order of development to the two previous videos. So I think the first thing that we can do is probably we can start by creating the grid of points. So let's start by doing that. The first thing I'm going to do is I'm going to add a comment. This is a really good practice. So for example, generate base points. And then here, I'm going to create an empty list of point3D objects that I'm going to call base points. And that's going to be a new list, something like this. Something interesting that I run a lot into is that people often think that point3D in Rhino Common refers to a point with 3 dimensions, but all points in Rhino have 3 dimensions. The 3D part actually refers to the fact that it's 3 doubles that are representing the coordinates of this point, as opposed to a different structure that exists in Rhino Common, which is the point 3f, which is 3 floats for the coordinates of that point. The difference between doubles and floats is that doubles have much more precision than floats, but they also take up more memory. So if you're working with like millions of points, you may want to do 0.3f because it's faster and cheaper. But if you're working with only a handful, 0.3D is perfectly fine. Okay, so now what I'm going to do is I'm going to create a double for loop, a nested for loop, that I'm going to iterate however many times in x direction, however many times I need of blocks in that direction, and in the y direction I'm going to iterate however many blocks I want in that other direction. So I'm going to say int j equals 0, j is less than however many elements, how did I call this? Count y, right? Yes, however many elements in the y direction I want, and then j++. Again, I still haven't recorded the videos that explain what a for loop is and how do you design it, but I will get to that at some point, and you will find links here or here or here somewhere whenever that happens, okay? And now I'm going to create another for loop for I equals 0, I is less than the number of elements that we want in the x direction, and I plus plus. And then at this point, what we need to do is we need to figure out the coordinates of this point. A good practice is to say, well, I'm going to create a variable called x. This variable is going to represent where this point should be in a space. And this point should be in a space probably if the point is the first one, the second one, the third one, or the fourth one, it should be that many times the distance between the blocks themselves, right? So that means that this is probably distance in the x direction times where we are in counting in that x row. So that would be I. Similarly for y, it's distance y times j. And then z is going to be 0, so we don't really need this here. We can create now a point 3D object called P. This can be a new point 3D with the x coordinate, the y coordinate, and 0, as we just created those two. And then to finish this, I can just add to the list that I had, I can just add this point that I created from scratch. All right. Let me run this first. If I run this, I see that there's no errors, so that is great, but I can't really see those points. I can't really see them because I need to output them. Of the component. So what I'm going to do is I'm going to start creating outputs here of things that are meaningful in my component. So for example, these are going to be, I'm going to call this like B points or ground points or something like that. Okay. And then as I do that, I'm going to go back into my component, and at the very end of the component, I'm going to say ground points is going to be equal to that list of points that I just generated, base points. As I do that, I'm going to press run, and you can see that those points show up here. I'm going to close. I'm going to add here like a generic data component so that I can like switch between them, and I can turn this off, and you can see that these points are the grid of points that I just created with these two for loops. And if I want more in one direction, more in the other direction, or if I want to tweak their distances, they are properly linked with these variables. So that's great. Okay, the next thing we're going to do is we're going to remove all the points that are outside of the curve from that list. So we're going to say clear points outside curve. I think call is a better word here. And before we do that, what we will have to figure out is whether if those points are outside of inside, or where they are in relation to the curve. If you remember, in the previous exercise, we did have this component called point in curve that gave us numbers. So if you remember, it didn't say true or false. It gave us numbers 0, 1, 2, depending on the relationship between the curve and the point. 0 for outside, 1 for coincident, and 2 for inside. You will see that in C# we are going to use a very similar technique. It's just going to involve like writing these things in a slightly different way. So let me get into that. What I'm going to do is I usually don't like modifying lists of data that I've already created because sometimes it can get cumbersome and it can get confusing. So if we're not working with millions of data, I think it's fine that instead of just cleaning the points from this list, what we do is we just create a new list with the clean points, with the cold points. So I'm going to create another list, cold points. That's going to be a new list of point 3D objects. And you will also see out there a lot of people, instead of declaring the variable as what it is, a list of 3D points, just writing var. This is a very common practice because it just so happens that the compiler, when you say here that what you're creating is a new list of point 3D objects, the compiler already knows that this variable should be of the type list point 3D. Okay, you will see that a lot out there. I'm going to try not to do that because I think from an educational point of view, it's nice for beginners, for people who are learning, to see what things are, as opposed to that general bucket of var as a keyword, right? So I'm going to try to stick to that unless someday I'm kind of lazy or brain dead, and at which point I will try to to do shortcuts. All right, but now the interesting thing is we can write a for loop, for example, but instead of iterating manually over each one of them, we can use a for each component, because now we don't need really the number of where those points are on the list. So I can write a for each loop where I say for each point 3D object P in the list of base points, then I'm going to check if that point is inside of that curve. Okay? So how do we do that? It turns out that curves have this property. What is this? Boundary. It turns out the points have this property called, where is it? It's here, contains. You can see that by using curve.contains, we can, where are you? Here. Yeah. You can see that we can compute the relationship between a point and a closed curve region. So I'm going to use this, and I'm going to open the overloads, and I'm going to go over, why are you flashing? I do not like all right. So, okay, so let's just look at this in the Rhino common documentation instead, which is probably a much better practice. So if you type Rhino common and probably curve contains, we're probably going to land somewhere there. This is a good one. Okay. I'm going to go back here to the method, and I'm going to see that the method has 3 overloads. It means that I can call it with either just a point, with a point and a plane, and with a point 3D and a plane, and a tolerance value. So if I click here, it tells me like this computes the relationship between a point and a curve. The curve must be closed and return the value, or the return value will be unset. I have the point as that I want to test. I have the plane to compare, and I have the tolerance. Okay. Do I have the plane and the tolerance? I mean, everything is in the world XY, so maybe I can use this one, contains, because it computes the relationship between blah, 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 and both the curve and the point will be projected to the XY plane. In this case, because I'm already in the XY plane, I can probably get away with this one. However, am I freezing again? It looks like I might be freezing again. Where we had a more complicated relation between them, then we would probably need to use this here. So let me get to that. So contains, and then the P that I'm going to use, and something very important. I would like to highlight that the return value, so what this method gives me, is this thing called point containment, which I'm not really sure what it is. Let me just write that here. So point containment PC equals boundary curve blah blah blah. Okay. I'm going to run this, see if it works. And I'm getting an error here. It's not an error, it's a warning. And it's telling me that Rhino point, the curve contains with just point, is obsolete. And it's asking me to use the version that takes a tolerance. That is probably going to be this third one here, the one that has a double. Okay, we'll get to that in a second. We'll fix that in a second. Let me finish this. Let me finish this before with this version, and then we get to that one. What is point containment? Point containment is this strange thing. So you can see the return value is of the type point containment. if I click here, you can see that point containment is an enumeration, and you can think as an enumeration as a list of numerical values that have names. So this list of numerical values can have the value of 0, 1, 2, 3, but the names for each one of those values is 0 is unset, the relation is meaningless, I don't really know what that means. For 1, the relation means that it's inside. For 2, the relation means it's outside. And for 3, the relation means that it's coincident. This is also very interesting because if you remember from here, in this one, the numbers are different. Here the numbers are 0 is outside, 1 is coincident, and 2 is inside. Whereas here, 2 is not inside, it's outside, and 0 is unset or whatever. So these kind of things are things that we need to keep in mind when we switch between vanilla Grasshopper and Rhino Common, because the authors that developed both frameworks may have had different opinions about certain things, and those reflect on how we use and how we have to pay attention to how the code is written. So what that means is that the points that we are interested in are the ones that have a point containment value of 1. Okay? How can we check that? Well, first of all, we can do something. Let me just output this here on the window and say for each one of these points, just go ahead and print pc.toString. If I do that, I'm probably going to get a full list of like points are outside, outside, or inside. You see this? This is actually pretty nice. This is what I meant by a list of values that instead of having numbers, they have names of sorts. That's what an enumerator is. But it's also great because what this means is that I don't really need to remember which number corresponds to inside or outside. What I can do is I can do something like this. I can say if PC point containment equals point containment dot inside, then take that point and add it to the curled points list. Curled points dot add this value here. As I do that and I press run, everything works well, but I can't really see anything. So what I'm going to do is I'm going to replace the output. Instead of base points, I'm going to just use the curl points, and boom! Now the output is just that list of points that contains only the ones that were checked for containment inside. Okay? As you noticed before, the compiler is complaining because the curve contains one single point 3D is a method that the authors of Rhino Common had flagged as obsolete. That means that very soon they will discontinue that method, and they're giving you like a warning so that you know that it's going to be cut off very soon from development, and that you would rather be better off migrating to a more modern version of that method. So I think it's a good thing to do. So why not? Let's just do that. So what we're going to do is we're going to go back to here, look at the documentation, and see that what this method contains with tolerance needs is it needs the contain, it needs the point, it needs a plane in which the curve lays, and it needs a value for tolerance. But do we have that plane? The question is, do we have the plane where the curve is? Right now, we know that that curve is inside of the xy plane, and we know that just because we created the curve that way. But whether if the curve was a little like off the plane, or if whoever created that curve did not pay good attention, then that would break our definition. So in order to do that, maybe what we can do is like we can actually take a look at the curve and check first if it's planar, and then find which plane it's inside, so that we create something that is a bit more resilient to input data that is not correctly formatted. So let's do that right now, and let's do that before we call the points and the curve. And let's write something that says here, I don't know, something like make sure curve is good. All right. So something that we can do, for example, is let's start by checking if the curve is planar, right? So I'm going to say if, what was the curve? Boundary curve is boundary curve. And then we can see a lot of things that we can access, a lot of properties and methods. So I'm going to go here where it says is planar. And then you can see that the overloads are just that, or it's asking me for a tolerance. So I'm just going to go for the basic value. And remember that what I want to check here is if the curve is not planar. And if it's not planar, I want the component to stop and give the user a warning like, hey, I can't work with this, I need a planar curve. So I'm going to say if the curve is not planar, so that's why I'm using this exclamation sign here, then I'm going to issue a warning or an error in this component. I'm going to make the component red. And in order to do that, C# scripting components give you access to an instance of the component itself. So there's this word called component that basically represents this C# scripting component that we are working in right now. And you can see that there are a lot of things that we can do with this component right now. We can bake geometry, we can figure out what the category is. This is much more relevant if you're working natively and if you're developing a Grasshopper plugin. But for the time being, the method that I want to add here is the add runtime message. If I open this, it tells me, it asks me for two things. First, what kind of level of error message I want to send and the actual message. So for example, let's say I want to say here, Grasshopper runtime message level dot, and here I can choose between a remark, a warning, or an error. So I want an error. I want to stop and say no, I need a planar curve. And I'm also going to add a return value here so that I make sure that the component stops executing and nothing else goes on. Okay, so that's going to be the first test. Let me see if this works. I'm going to hit OK, and everything works fine because this curve is planar. But let me create a curve that is not planar. Where is the object snap? Yeah, I'm going to close this. F10, I'm going to drag this point off plane. All right, and I'm going to drag this point off plane as well too. And now I see that this curve is non-planar. Let me bring this curve inside of Grasshopper, and then as I plug it here, boom, I get the component goes red, I get an error, and then this error gives me the custom error that I just described. No, I need a planar curve, all right? And then nothing else goes on. You can see that the points were not generated. So this is a good thing because we're checking our inputs for sanity if they fit our requirements, and then we're giving the user good feedback about, oh, we just can't work with this. You have to give me a planar curve, okay? So these kind of things are usually really good practice to implement. Okay, so let me go back to normal, and I'm going to delete this nasty curve. And now, now that we know that the plane is curved, we can probably find, now that we know that the curve is planar, now we can probably find which plane that is and use that plane for the containment. The next thing we're going to do is, now that we know that the curve is planar, now we need to find that plane. Okay, that's going to be super easy to do. I'm going to open here, and here you will notice that if I say boundary curve dot, there is a method called try get arc, circle, ellipse, plane. Let's try to get a lot of things. You can't see the tooltip is overflowing on my other screen. But if you see try get plane, you can see that this component tests the curve for planarity and return the plane. We could have used just this to see if the curve is planar, but I think it was a good exercise to do anyway. I want to point out that the return type is a Boolean. So this method tells me whether if it was successful getting the plane or not, but the actual plane, I have to get it through an out reference, So I want to say that, I want to do that, and I want to say here, for an out, I need to store the result of this computation on a plane object. Something that I can do is I can create, for example, a plane called curved plane here. And then here in the out, I can say, store the result of that computation outside here on curved plane. Is that correct? Yes, that's working good. That's working good. And now that I'm here, now that I do have the plane, the curved plane, I can substitute this obsolete method and say contains is going to, remember, is going to take 3 parameters. It's going to take the point, it's going to take the plane of the curve, and it's going to take tolerance. So the point is going to be P, the plane is going to be curved plane, and then tolerance is going to be some value that some small value, so 0.001, for example. As I do this, you see that I don't get the warning message anymore because I'm using the most modern version of that method, which it's nice. Okay. The next thing we're going to do is, now that we have all the points inside of the curve, we're going to implement the same logic that we did in the previous video, where we're going to randomly remove some of those blocks, but the probability of those blocks to be removed is going to be larger the closer they are to the curve, and with a random probability. So what we're going to do is we're going to create another list of points, and we're going to compare for each one of those points the distance to the curve. We're going to compute that distance, and then as we do that, we're going to create a random value, and then we're going to figure out if we should remove that point from the list or not. So let's get going with that. I'm going to go here, and I'm going to say call points very close to the curve. So what is the first thing that I need to do? Well, for each one of these points, well, first of all, I'm going to create another list of points, point 3D, random called points. This is a terrible long name, but whatever. I'm going to create a list of point 3D objects. And then what I'm going to do is I'm going to go over all these called points here, and actually, maybe I could do this inside of here. We could probably mix both things. We could probably mix containment, and we can probably mix figuring out if they should be randomly removed. But I'm just going to keep them separate just for the sake of clarity, okay? So what I'm going to do now is I'm going to go over all the points here in the called points list, and then I'm going to compute the distance to the curve, and then I'm going to work with that. So for each point 3dp in called points, first of all, I'm going to compute the distance to the curve. The way to do that is actually by first figuring out what is the closest point to that to that point on the curve, and then computing the distance between the 2 points. So I'm going to create a point 3D object, closest point. Oh, my laptop is doing a really weird noise. I hope it doesn't blow up. Point 3D closest point, and here I'm going to find what is the closest point to that curve. So what is that going to be? I'm going to look first at the curve, because I don't remember how this was. Boundary curve dot closest point. Yeah. Finds the param. Okay. So good. So what I need here is, if you look at the documentation, it tells me that it needs a test point, but what it gives me is the parameter along that curve where the closest point is. The parameter, you can think of it as the relative distance, sort of, within the curve. It's basically a number that tells me along that curve where that point is situated. Okay, that is one overload. The other one has an additional value, which is maximum distance. If I want to nudge, if it's too far away, then I just don't check. And you can see that the parameter is given to me as an out reference. So I'm going to need to first here create double, what is the parameter t? And then here, this is going to be the reference point, and I want the parameter to be output here to this double. So now after this, t will have the value of the parameter at which point that point on the curve is. As I do that, now I know how far along the curve that point is. What I need to do now is I need to actually get that point. So point 3D, point on curve, that's going to be boundary curve, point at, yes. You see, this evaluates a point and it gives me a point at a center parameter. So it's going to be point at t, and this point here is going to be the point along the line, along the curve, that is going to be the one that is closest. I'm just gonna, so that for the sake of visualization, this is not what we need to do, but I'm just gonna say random call points. Please add this point that I just created here. And I'm going to output that out of this component. And you can see that, boom, I got an error. What is it? Oh, it's a typo. So here, point 3D, you can see, yes, remember here, remember when we did closest point? Here, we also did get like a similar thing. So these are all the points on top of that curve that are the closest to all the points inside of the grid. Now, for each one of these points, this is not what I want. So for each one of these points that are on the curve, now I can compute the distance. Double distance is going to be the distance between the point that I'm checking, P, and the distance to the other point that I am comparing. So distance to PTC, that's the point on the curve. If I do that, maybe I can, just for the sake of visual output, I can print this to the console. Oh, sorry, distance. I'm going to print distance here to the console. You can see that I have a list of all the values of the distance between the grid points and their closest points on the curve. All right, so it looks like things are going well so far. And now the next thing that I need to do is I need to make sure that the points that have a smaller distance to the curve have a higher probability of being called. So the way we did that in the previous video is by calculating the inverse distance. So I'm going to do inverse distance is going to be 1.0 divided by distance. And if I print that now, you can see that, well, I'm going to print both things. I'm going to print this plus white space, and I'm going to print invert distance. And as I do that, you guys can see that I get both the original value and the inverse. So you can see that when the value is small, the distance is small, the value is higher, and when the value is higher, when the distance is higher, the value is smaller. Okay, now the final thing that we need to do is we need to compare this inverted distance with a random number, and if this value is under that random number, then we can remove that from the list. So how can we do that? In the way we do randomness in C# is with the random object. So we can create a random object RND, and then this random object, you can think of it as a random number generator. So from this object, we can always ask for random values over and over again. So for example, if I say here, double R is going to be RND, can you please give me, and you see that it has next bytes, and it has next double. The random component is actually very simple. It gives me here, when I say next, it tells me that it can give me a random number which is a random integer, which is either 0 or 1, a random integer between a minimum value and a maximum value, and a random number with but that's only for integers. For doubles, for precision, I want to use next double. What's interesting about next double is that it will always give me a random value between 0 and 1. And remember that if we're talking about probability, then maybe we want to maximize that. So I want to say, I want to multiply this by 100 so that the random value has a range between 0 and 100. Okay? And I'm going to add this here to the output. Random value is going to be equal to, this is going to have nothing to do with this, but I just want to show you how we have generated random values from 0 to 100 by using the random object. Okay? If you remember from the previous video, what we found was that having a value of 100 for the probability was a really large number, because since we are inverting values, it's very unlikely that any of these values is actually going to be greater than 100, or is going to be in that range. So this is not going to be a really good range domain for us to work. I'm going to implement that anyway, and then we're going to go back, and then we're going to work with this number and make it an input so that we can control the amount of that variation. So the rule would be, okay, if inverted distance, which is this value that we have changed here, that we have inverted, if this is greater than the random value that we just generated, then what I do want is, to the random call points, I want to add the point that we are checking right now, which means that the point that we were checking for proximity passed the test. It was very far away, and therefore it was not randomly eliminated. So I want to keep it in my list. As I do that, I can show you how random call points is going to basically, oh, there was an error. What just happened here? Random if, oh no, sorry. If this is under the threshold, sorry, then we are good. Okay, so you can basically see how all points are inside of that threshold, because if I flip it, basically no point is inside of that threshold. So the problem is that the value of 100 numerically is too large for the computation that we're doing. So we may want to add here some kind of probability to slow that down. I'm going to call this maximum probability. And it's going to be of the type, I'm going to make it type double, all right? I'm going to write here something that goes from 0 to 100, and I'm going to go all the way down to the value of 2, for example. And I'm going to plug that in here. This is going to be maximum probability. And you can see that as I do that, some of these values start popping out. So if I go high, then they basically disappear right away. But as I go down in this maximum probability, you can see that there's a higher chance that they disappear. And look at how nice is this. At 0.16, you can see that almost all the points that were very close to the boundary disappeared, and many of the ones that are inside also did disappear. Let me change the range of this to 5, for example, so that we have a bit more precision. And you can see how this is very nice. This showcases that the algorithm actually works. At 0.03, only the ones that are very far at the center are surviving. And as we keep growing, you see how they are getting better, until we get something, for example, like 2. No, I kind of like this value here. I'm gonna keep it here. I like 1. Let's say 1. Boom. Okay. And another thing that I want to add is I want to add a random seed. What does that mean? I want to add a value so that I feed into, I want to add a value that I feed into the random number generator, so that I know that for some integer value, I know that for the same seed value, I will always be getting the same random number output. So what I want here is in random, I want to add random seed, and therefore I will know that whenever I change this, the combination of the random values is going to be different. But whenever I choose 100, I'm always going to get the same result. So you can see that if I change to 0, but I go back to 100, you can see that I did get the same gaps. So it's a number, in a way, the random seed is a way of making sure that you always stick to the same pattern of randomness, in a way. All right? Okay. The next thing we're going to do, we are going to take all these points that are now clean and inside of the boundary and like randomly cleaned up, and we're going to project them to the surface on the bottom that we want to be the ground plane. How are we going to do that? I'm going to clean up some of the code here, and I believe that we can do something where we take all those points and we project them. Let me look in Rhino Common. Project points, intersection, project points to B reps. I like this one. Yeah. So we have project points to B reps. It gives me an array of point 3Ds as opposed to an array list. It's a static method, and it needs a list of B reps, a list of points, and direction and tolerance, which I think we all have this. This is the main reason why when we chose what kind of input type our C# component was going to have, instead of choosing surfaces, I chose B reps, because B reps in Rhino Common are, to my taste, it's a structure, it's a class that is used way more widely across all methods than surfaces. And I believe that B reps actually do contain lists of surfaces inside of them, and they're trimming information. So it's just, I just happen to end up working with B reps most of the time rather than working with surfaces. So this was a good example of that. So this is project point to B reps. So I'm going to say, well, I want to point 3D objects. So points on the bottom, and this is going to be equal to what was it called? Project points to B rep. And then as I open here, I can see that this is not really recognized. In Rhino geometry, and this belongs to Rhino geometry intersect. So I may have to add the full signature of this method to be recognized by Grasshopper. So let me do that. So instead of this, I'm going to write Rhino geometry intersect dot project. Where are you? Come over here. Project here. Project points to B rep. I don't know why it's not working. Maybe IntelliSense is not working. But let's just do it. So I'm gonna take bottom surface. I'm going to take the list of points. It's going to be, so what are the, yes, so a list of B reps. I don't have a list of B reps. I only have one, but I'll get to that in a second. The list of points that I want to project. So that's going to be the random call points. I'm going to add them here so that it's easier to read. Then the next thing is going to be the direction for the projection. That is going to be pointing down. So that's going to be vector 3D dot, for example, c-axis, and I'm going to invert this so that it's pointing downwards. And then the other value for tolerance is going to be something like, I don't know, 0.001, for instance. I'm going to run this, and as I run this, I'm probably going to get an error. Yes. Rhino geometry intersect. Are you missing an assembly reference? Why? Project points to B reps. Why is this not working? Do I need to import this? using, do I need that? Oh no, sorry, because there is another signature. There's Rhino geometry intersection and then point. Okay, my bad. Okay, so here, that's why it wasn't popping up. Okay, so intersect dot intersection dot project points to, there you go. Now it can see it. Okay. All right. So now we're good. Project points to B rep. Now we have the full, and we do that. And as I thought, yes, this C# is getting confused between the this needs to be a list of B reps as opposed to one single B rep. We could create it here. Project points to bottom surface. We could create it here, but because I'm just going to use it once, I'm just going to create it on the fly. So what I'm going to do is I'm going to say new list of B rep objects. New list of B rep objects, and then right away I'm going to use curly brackets to feed it with one single element, bottom surface, and this way I'm just creating on the fly a new list of B reps with this one element already in that list. As I do that, this is probably going to work. What is the output? I can't really see this yet, but I can see that if I change this and I put it here, the points in the bottom, now I can see that I have all those points projected on the bottom of my surface. That's pretty good. Can we do the same for the ones on top? Yep, so let's do that. I'm just gonna copy. Be careful with copy pasting. Copy pasting is the devil. It will always give you problems, and you will never. And they're really hard to debug. Okay, so try to avoid copy pasting because you always forget that you needed to change something, and it's gonna be terrible. So points on top. This is gonna be top surface. Random call points. This should be a positive z-axis. So that's good, and I'm going to substitute this to see if it works here. And yes, I do have all the points on the surface now, on the top surface. So I have points in the bottom and points in the top. Good. So probably, yeah, so we're probably ready to move on to working with the planes on the bottom. Planes in the bottom. The first thing we're going to do is we're going to create, we're going to add a comment because it's really good practice. Planes on the bottom, all right? And I'm going to create a, here, you see, that's a really good, interesting question now. Here, I could create a list of planes, or I could create already an array of planes because I know how many planes I'm gonna have. I'm gonna have as many planes as points bottom and points top. I would typically use a list because I'm a little lazy with typing, but for the sake of, for the educational purpose of it, I'm going to choose to create an array instead, so that you guys can see how that can be done. So in this case, I'm going to say I'm going to create an array of plane objects called base planes, for example, base planes, and this array is going to have is going to be a new array of play objects. And remember that here I need to add, I need to specify the size of this array. The size of this array is going to be equal to the size of points in the bottom. So that's going to be length here. Okay. And now that I have that, what I probably want to do is I probably want to start with a plane that is parallel to world XY. So for example, I'm going to create a for loop where I'm going to go is less than base planes dot length I plus plus, and here I'm going to say plane PL is going to be equal to plane world XY, and base planes dot I is going to be equal to PL. Okay. I probably want to keep the points there, so I'm going to create a new output, which is going to be planes, for example, and and I'm going to switch that here. And here, where it says planes, I'm going to output base planes. As I do that, nothing happens. I'm not sure why. Base planes. What is going on? Why am I not? Oh yeah, they are here. So why are they not showing up? Oh, okay, because they're all in the center. Because I did not use the bottom points as centers for those planes. That was lame. Okay, so pl.origin is going to be equal to, for example, points in the bottom dot I. And yep, and here they are. Now I have horizontal planes on top of each one of those points on the bottom of the surface. Okay, so we're good. One of the last things that we need to do now is we need to take, like we did in the previous video, we need to take all these planes that are all aligned and on the same, and they're all perfectly horizontal. And what we want to do is we want to tilt them a little bit to give these boxes that we're going to create on top of them, we want to give them like a little bit of a slant, okay? In order to do that, remember from the last video, what we're going to do is we're going to take the x vector of those planes, we're going to rotate it randomly, 360 degrees, and we're going to use that vector as the rotating axis for those planes, which will be rotated also a random value between 0 and some maximum angle. So let's do that. Before I decide to store this plane in the base planes, I'm going to start messing with it a little bit. So the first thing I'm going to do is I'm going to take the x, I'm going to fetch the x axis. So that's going to be, it's going to be from PL is going to be what is it, x axis. Okay, the next thing I'm going to do is I'm going to rotate that vector around, I'm going to rotate it a random value between 0 and 360 degrees. And then yes, so let's do that. I'm going to create a random angle, and this is going to be, I'm going to use the random object that I had before, RND, and I'm going to ask for, from here, I'm going to ask for a random double number. But remember that I want that next double is always going to give me values from 0 to 1. So I need to amplify that to go from the range of 0 to 360, which is just as easy as multiplying this by 360. Okay? And then what I can do after that is I can say, I'm going to take the vector and I'm going to rotate it around around a rotation axis. So one thing that I want to note here is that if you can, as you can see from the autocomplete and from the help text, the angle has to be in radians. So I cannot use the random angle in 360 that I used before. So I will have to change that to radians. And also the rotation axis that you can see there is going to be the z-axis, because I want, since the planes are horizontal, I want to rotate around the z-axis. So let's fix that. I'm going to go here and I'm going to say I want the random number to be a value between 0 and and then value of pi. However, if you remember from my other videos, I'm a really firm believer in Taoism, which is a mathematical belief that it means that we should all probably just start working with 360 degrees being 2 pi radians, which is kind of convoluted to say. So I'm just gonna treat myself to a nice constant here called tau, which is going to be 2 times math pi. And then here, I'm just gonna say tau times next double. This is not a joke. If you Google Tau Day or the Tau Manifesto, you will be able to read a lot about this. Okay, So I'm going to rotate this vector around the random angle here. And then the axis is going to be the z-axis. So here I'm going to go for the z-axis. So now I have a random vector that I've rotated 360 degrees, and I want to use that vector to rotate the plane. So what I can do is I can probably say PL rotate, and I do have a lot of options now. I have sine angle, cosine angle, and an axis. I have an angle and a vector. I have an angle, a vector, and a center of rotation, and blah, blah. So this is probably the one that I want to choose. So I want to choose around, I want to rotate a custom angle around a custom axis and a center, the center being the center of the actual plane. For this, I need to generate first, I need to generate a random angle. And remember that that is something that we wanted to control from the outside. We wanted to give the user the possibility of choosing the maximum angle for the tilting. Okay, so I'm going to add that to the inputs of this component here. So here I'm going to add a new parameter called maximum tilt, and this is going to be of the type double. And here, for example, I'm just going to copy paste this, and right here maximum tilt, I'm going to start with a value of 5, for example, but we can check later if it's good or not. And then so here, where was I? I was rotating the plane, but first I need to find a random angle. So double random tilt angle, that's going to be also random next double, which, remember, from 0 to 1, now I'm going to amplify it for the value that I just got. So maximum tilt times the value of 0 to 1. And now that I have that, I can rotate the plane. What am I going to rotate? I'm going to rotate it around an angle. So that's going to be random tilt angle. And then the axis is going to be the vector that I just rotated, Vx. And the center of rotation is going to be the center of the plane. So PL dot origin. Okay, one thing to note here. This rotation takes the angle in radians, but here in max tilt, you see that this would have been like something from 0 to 90, for example. This, I am taking it as probably as degrees, right? So what I need to do, I need to convert the maximum tilt value to degrees, sorry, to radians, before I compute this maximum tilt angle. That is very easy to do by saying, take this value, multiply it by tau, and divide it by 360. Okay, but since those two, tau divided by 360, are always going to be the same, we can save ourselves a tiny bit of calculations by just saying, let me create a variable that is going to be called 2 degrees. And this is going to be the value of tau divided by 360. And now I can just replace this here. And I have saved myself a 1 multiplication for each iteration of the for loop. It's not great, but it's much easier to read. So I think we're good here. And as I do this, are the planes going to rotate already? Are they rotating? So let me see. What if I crank this up to 90? Am I getting those rotations? Yes, I am getting them. Okay, so it's just that with the value of 5, it's just very subtle. Okay, so those planes have also already have the tilt, so we're almost ready. And finally, the last thing we're going to do is, now that we have the planes in the right position on the bottom and with a nice tilt, then we're just going to place boxes on top of it, which is going to be by far the easiest thing we're going to do in this tutorial. So let's get to it. I'm going to create a new output. So that's going to be, for example, the blocks, so which is what we actually want to do here. And all the way at the end here, I'm going to create concrete blocks. Now, should I create a list or an array? It doesn't really matter. You choose one or the other. I'm just gonna use a list in this at this point because I just I'm a little it's kind of late and I'm a little lazy. So I'm gonna create a list of boxes that I'm going to call boxes new list blah 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 and and now I'm going to iterate over each one of the planes in that I have designed before. So for each plane PL in base plane, now I'm going to use that plane to create a box. How did I create boxes? I guess with the box constructor. Let's see if that works. Box B equals new box. Yep, and what can I do? I can create a box from a bounding box, from a base plane, and 3 intervals. I like that. From points, from base geometry, and from what? Nah. So I'm gonna stick to this one. I like this one a lot. So I'm going to use new lines to make things clearer. So I want to create a plane. I'm going to create a box from the base plane and 3 numerical ranges. So the base plane is going to be PL. The interval, the x size, is going to be a new interval, which is going to go in the x direction. Is going to go from we had the dimensions of the boxes as inputs. So we have what did we have? We had block width and block depth. So then this interval is going to be, it's going to go from minus block width to positive, sorry, from minus half the block width to positive half the block width. So that's going to be minus 0.5 times block width and to 0.5 times block width. The y is going to be very similar, but it's going to be block depth instead. And what is the C height of these blocks? The C height is the distance between the planes in the bottom and the planes on the top, which I kind of forgot to compute. Okay, so I guess I'm just gonna give it like a value right now so that we can finish this. But we'll have to get back to this. So boxes dot add the box, and then here what it says blocks is going to be equal to boxes. There's some kind of error here. So let's see what's. You cannot convert from int to Rhino from interval. Yes, so because I have to create a new interval from 0 to 1, for example. And I'm starting at 0 because I want my boxes to be sitting on the plane and start from there. So I'm going to do that, and you can see that I have like all these boxes that are like 1 unit high, and you can see that the tilting is much noticeable right now, right? Let me, oh no, wait. So the block width, yeah, the block height, the block depth, and then the tilt, maximum tilt is going to be 2. But you can see that as I crank that up, the boxes start like tilt. That's kind of cool, actually. I actually like that a lot for some reason. Anyway, so we need to calculate the distance between the 2 planes. So we could do that in 2 different ways. We can create an array of doubles that represent those distances, or we can just do it here in line. I think we're going to do this here in line, but because I've been working with the points in the bottom and the points at the top as arrays, I think I'm going to have to switch to arrays here because I'm going to need the iterator, the value of which plane are we talking about to compare them together. So I'm going to switch this to arrays, and it's going to be a new box array of how many points? Well, as many as we have base planes, length, and here I'm going to create a for loop where I'm going to iterate over all the base planes, And because I do have the exact same number of base planes, bottom points and top points, the for loops are going to match. So that's why I can do this. I can say double distance is going to be equal to where are these points in the bottom, element number I dot distance to points in the top, element number I. So with this, I can calculate each one of those values. Then I can create the box here. And then here I'm going to replace 0 with that distance. And then I can now say, well, this plane, I don't really have this plane. So this is going to be, I'm going to have to replace it with the base planes, element number I. And then here, I'm just going to have to say boxes element number I is going to be equal to this box that I just created. And as I do that, ta-da! Woohoo! We're done. All right, let me tweak a couple of things here. The maximum tilt is going to be 2, so that we can see that there is still like a little bit of tilting, but it's very subtle, which I kind of like. I'm going to use again the display component. Where was this? I'm going to use this to render the boxes, but instead of leaving them pink this time, I'm going to create them. I'm going to make them gray, I think. Yes. So can we do gray here? Yes. And then can we do a shaded? Is that the one that is nice? No, it's Arctic is the one that it's. Okay, this one. Yes. Oh, and this one, I need to remove this one. Okay. And these things here, and I can remove this curve. I can remove this curve. I don't know what I did. Oh yeah, I can't really remove. I have to hide it. Sorry. Hide the curve, and then here, the base, not the top plane, no, the base plane. Yes, I could fit this here as well, and just have it as part of. There you go. So there we have it. Our monument. I mean, obviously the scale and the proportions are not great as compared to the real thing, but the spirit is right there, which I kind of like. All right. So that was it. I think this was part 3 of replicating this monument with a pure C# logic in one single large component. The question is out there. I don't really like writing very large components. I think an interesting thing could have been perhaps to like break down the whole process in several components, several C# components that communicate with each other with their inputs and outputs. But for the sake of testing, I think this has been, but that's like another conversation that we could have in the future. So that was it. I will post this code somewhere. There will be a link somewhere in this video description to where you can download this and maybe like clean it up and make it look a bit nicer. I will leave that exercise up to you. Thank you very much for watching this tutorial, and I'll see you somewhere in some other one.